If the fluid is flowing in a path, the fluid is flowing and we need to find any force at any point, then this fluid dynamics can be used to determine the force at any point. If we consider mass and force in our analyzation, that is called as dynamics. We are dealing with the fluid, so it is called as fluid dynamics. In this fluid dynamics, three major laws, universal laws. These are universal laws that exist in nature. Those are conservation of mass, conservation of energy, and conservation of momentum. The first thing is conservation of mass. We have seen in the continuity equation. In this video, we will see about conservation of energy. And this conservation of energy is represented with Bernoulli's equation. And next is conservation of momentum. We will see in the coming classes. In order to understand the dynamics is generally consisting of forces. So forces are of three different types: body forces or volume forces. Body forces can also be called as volume forces. And there is surface force and there is linear force. You know that if we join the points, a one-dimension figure is formed. If we join these lines or one-dimension figure, then area is formed. If we join areas, a three-dimension figure is formed. So forces that are proportional to length are called as linear force. Forces that are proportional to area, that are called surface force. Forces that are proportional to volume are called body forces or volume forces. So linear force, that is proportional to length. So the example is surface tension. And in surface force, proportional to surface area, the forces which act on surfaces. So those are pressure force, shear or tangential force, and turbulent force. And body force, proportional to volume of the body, the weight of the body which acts downwards, and centrifugal force, if this is the center, and if it is rotated, then centrifugal force act outwards. That depends on the volume of the body, so that is also a body force. So these are the different types of forces. So these forces, the forces are given by different scientists by considering different types of these forces. So by Newton's second law of motion, we know that F is equal to ma. This F is the net force. If different number of forces are acting on a body, the resultant or the net force of all the forces will lead to a acceleration a of a mass of a body of mass m. So what is this net force? This net force is composed of different types of forces: Fg plus Fp plus Fv plus Ft plus Fs plus Fc. So this Fg is called gravity force, which is also called as weight of the body, and Fp, pressure force. These are generally the forces that we consider for fluids. So this pressure force, which acts in compressive direction, so pressure force, and next is viscous force, turbulent force, and surface tension force, and compressible force. So these are all different types of forces that may be acting on the fluid. If all these different types of all these forces are considered, then it is called as Newton's second law of motion. Then Reynolds equation of motion. So he neglected compressible forces and surface tension forces. So this Reynolds equation is valid for incompressible fluids. So Reynolds equation is valid for incompressible fluids. So F is equal to, this is net force. Net force is equal to gravity force, viscous force, pressure force, and turbulent force. And next, Euler gave another equation. We will study about this Euler equation and Bernoulli's equation detailedly. So Euler equation is flow is assumed to be ideal. Ideal flow means no viscosity, and incompressible, and what are the no friction, so no surface tension. So these are if these characteristics are possessed by a fluid, then it is called as ideal fluid. So in ideal fluid, only two forces will be acting. Those are this gravity force and pressure force. So gravity force plus pressure force is equal to net force in case of Euler equation. And next, Navier-Stokes equation. If adding viscous force to this Euler equation gives us Navier-Stokes equation. So this is Euler's equation plus viscous force gives us Navier-Stokes equation. So Euler gave equations of motion. So what are these? So these are the equations of motion. This B represents body forces per unit mass in x, y and z direction. So what are the body forces? The gravity force is body force. So gravity force is body force in case of this Euler's equation, since F is equal to Fg plus Fp, gravity force and pressure force. So Bx, By, Bz are the components of body forces per unit mass in x, y and z direction. So this Bx is in x direction, By is in z direction and Bz in z direction. So the units of Bx, By, Bz, Bx, By, Bz, the units are Newton per kg. So per unit mass, the forces are Bx, By and Bz. So these are the equations that are given by Euler. Sorry, here it is dp by dx. I wrote d rho by d. So bx minus 1 by rho dou p by dou x. This dou p by dou x is pressure gradient in direction of x, which is equal to dou u by dou t plus u into dou u by dou x plus v into dou u by dou y plus w into dou u by dou z. If you see this right hand side of the equation, that is equal to acceleration. So acceleration in x, acceleration in y, and acceleration in z direction. From these all equations, we can write in the vector form as, so b bar, which indicates x, y and z directions. B bar, that is a vector, minus, and here minus 1 by rho dou p by dou x, dou p by dou y and dou p by dou z. That is del p, which is equal to acceleration. So this is the Euler's equation. So remember this, you can write these all three equations from this single equation. So this is the body force per unit mass density, this is pressure gradient, and this is the acceleration. You don't need to derive this, just remember the Euler's equation of motion. So where can this Euler's equation valid? For compressible and incompressible flows, Euler's equation can be applied. For non-viscous flows, or non-viscous flows are also called as inviscid flows, the Euler's equation can be valid for rotational and irrotational flows, steady and unsteady flows. So for compressible and incompressible, so the density is present and we can apply this both for both compressible and incompressible. And for non-viscous flows also it can be applied for rotational and also irrotational flows. For steady, so here dou u by dou t is present. Dou u by dou t is present means unsteady flows. If it is not present, then we can apply it for steady flows. So that's about Euler's equation of motion. Then next comes Euler's equation along a streamline. So those are the Euler's equation for any flow. If along a streamline we need to find Euler's equation, then see this diagram. This black color line indicates the streamline, and we have considered a little fluid element in this way, which is in cylindrical shape. You can consider any shape. I'm considering it as a cylindrical one. So the cross-sectional area is delta A, and the length of the fluid element is delta S, and the distance from this point to this point is delta Z. So here, this red color forces is indicating the weight of the body, weight of that fluid element, and this orange color one is indicating pressure forces. So here, if here there is pressure force P, here there will be pressure force P plus dou P by dou S into delta S. So pressure changing with respect to this S and multiplied with the length delta S. So that is the pressure acting on it. So what will be the pressure force? Pressure force will be into delta A, here also into delta A. So these are the forces acting. If we resolve this weight is W, and let me say this is alpha. So this is W, this is alpha, and this is another one perpendicular to this line. So what will be the force along the, what will be the weight along the streamline? That will be W cos alpha. So this will be W cos alpha. I am considering this direction as positive and this direction as negative. So balancing these forces, what do we get? So next external force that will be acting is net force F along the streamline Fs is equal to, so what are the forces? This is P into delta A, P into delta A. This is positive direction and this is negative one. So minus P into delta A minus dou P by dou S delta S into delta A. So that is negative direction. And there is weight minus W cos alpha. So this is the force balance equation, and cos alpha can be written as, so if this is alpha, this will also be alpha. So cos alpha is equal to, so adjacent divided by hypotenuse. Adjacent is delta Z divided by delta S. So but this is the exaggerated figure, but fluid particle means an infinitesimally small. So limit delta S tends to 0, delta Z divided by delta S. This will be the cos alpha. Since alpha is everywhere different, so at a particular point this will be the cos alpha. So that will be dz divided by ds, d by ds of z. So that is cos alpha. And also F is equal to ma. We know this. So Fs, in this case Fs is equal to mass. Mass can be represented as rho g into rho into volume. Volume of this cylinder that we are consider is delta S into delta A. So this is the mass. And acceleration can be represented as dv by dt. So capital dv by capital dt is called as acceleration. So if we substitute this in this, rho into delta S and delta A, dv by dt is equal to P into delta A gets cancelled, and the remaining is dou P by dou S delta A minus W. Weight can be written as rho G into volume. Volume is delta S into delta A into cos alpha. Cos alpha can be written as dz by ds. So from this, delta S delta A gets cancelled on the both sides. So here we can write rho dv by dt is equal to minus dou P by dou S minus rho G into dz by ds. And also we can write this dv by dt as, I am taking rho this side, so dv by dt is equal to minus 1 by rho dou P by dou S minus G into dz by ds. And this dv by dt capital dV by capital dt, material, this is called as material derivative, that can be written as dou v by dou t plus v into dou v by dou s. So this can be written in this way, is equal to minus 1 by rho dou p by dou s minus g into dz by ds. So this is called as Euler's equation along a streamline. Euler's equation along streamline. So why did we find this? Bernoulli's equation is the integration of this equation along the streamline. So Bernoulli's equation is obtained by integrating Euler's equation along a streamline. So what is Euler's equation? We have found here dou v by dou t plus v into dou v by dou s is equal to minus 1 by rho into dou p by dou s minus g into dz by ds. So this is what Euler's equation along the streamline. Euler's equation along streamline. So Bernoulli integrated this equation and found his own equation, Bernoulli's equation. So this equation is integrated for steady flows. So let's see the validation of Bernoulli's equation. It is for steady flows only. For unsteady flows, it cannot be applied. So this is derived for Bernoulli's equation only. Sorry, Bernoulli's equation is derived for steady flows only. And for non-viscous flows, non-viscous means inviscid. For inviscid flows, it has been integrated. So for rotational and irrotational flows, and for incompressible flows. This is first derived for incompressible flows. Later on, it can be applied to compressible flows also. So let's see what is Bernoulli's equation by integrating this. So here, dou v by dou s. This term we can consider it as dv by ds. dv by ds, since the velocity is only a function of this streamline coordinates. So we can write dou v by dou s as dv by ds. We are considering this Bernoulli's equation as a steady flow. So this will be 0. So v into dv by ds is equal to minus 1 by rho dp by ds. This pressure is also only a function of that streamline. So g into dz by ds. If we integrate it, integration v dv by ds with respect to ds. So with respect to why with respect to ds means in terms of energy we need to derive. In terms of energy means force into this traveled distance. So that is called as work done. Work done can be energy. Due to supply of energy only work can be done. So we are differentiating with respect to we are integrating with respect to ds, which is equal to minus 1 by rho integration of 1 by rho dp by ds minus integral g dz by ds. So ds gets cancelled, ds gets cancelled, and here also ds gets cancelled. So integral v dv is v square by 2 is equal to minus integral of dp by rho. Since we don't know about this density, whether it is compressible or incompressible, so I am putting this rho inside the integration minus integral of, so integral g dz is g into z, since g is a constant, plus constant. So integral dp by rho plus v square by 2 plus gz is equal to constant. This is called as Bernoulli's equation. Bernoulli's equation. This can be applied for compressible also. Steady, compressible. So if we need for incompressible flows, rho comes outside and 1 by rho, p by rho plus v square by 2 plus gz is equal to constant. This is for steady, incompressible flows. This can also be represented as, if we multiply or if we divide with g, that will be p by rho g plus v square by 2g plus Z is equal to constant. This is the popular one. So we will be using this equation. P by W, this rho j can be written as small w, specific weight. So P by W plus V square by 2j plus Z is equal to constant. For ideal flows, P by W, P1 by W1 plus V1 square by 2g plus Z1 is equal to P2 by W plus V2 square by 2g plus Z2. This is for ideal flows. There is no friction in case of ideal flow. If P1 by W plus V1 square by 2g plus Z1 is equal to P2 by W plus V2 square by 2g plus Z2 plus head loss. This is for real flows. So what are these values here? If there is any flow, so if this is a pipe and here the pressure is P1, velocity is V1, and this height is from any datum, it is Z1. Here the pressure is P2 and velocity V2, height is Z2. So these are these values in this case. We can see that this left hand side and right hand side, those are the, we can say that those are energies. So energies are balanced. So this is called as conservation of energy. Conservation of energy. So Bernoulli's equation is the best representation of conservation of energy in fluid mechanics. Here, this is called as pressure head. Pressure head. This is kinetic head. This is called as datum head. So these all are in terms of meter, in terms of length. And also there is another one, piezometric head. This piezometric head is equal to sum of pressure head and kinetic head. So that is called as piezometric head. In the next video, we will see about applications of Bernoulli's equation. So different instruments that are constructed with the help of this Bernoulli's equation, we will see about that in the next video. Thank you.